Welcome to the 9th lecture of the course on non-traditional abrasive machining processes. Today we are going to deal with ultrasonic machining, effects of various inputs on the outputs, etc., and other subjects also, which in order to complete everything, there are some other things that I have included. So, starting with the effects of the different inputs, we had already started this thing in the last lecture, but we had to stop in between. So, I will just recapitulate the first two graphs and move on with the rest of the graphs. We had first come across a diagram in which we are seeing the effect of average grain size on the surface roughness created on tungsten carbide and glass. So, glass and tungsten carbide here, they are the workpiece materials, and average grain size basically means the average abrasive grit size. So, it basically means that I am increasing the grit size and I am checking up the effect of the grit size, increase in grit size on the surface roughness which is produced on tungsten carbide and on glass. The first and foremost thing that we notice is that with the increase in grain size, the surface roughness is increasing. That means, it is becoming more and more rough. However, the effect is more pronounced on glass. So, let us first let's check up these two things separately. First of all, why should surface roughness increase with average grain size? For that, let us have a quick look at this particular diagram. This is one grain, this is another grain, and the roughness, corresponding roughness that it will produce will be corresponding to the crater size. Okay. So, this one will be producing this particular crater, this will be producing this particular crater, of course, on brittle materials. So, glass is brittle, tungsten carbide is brittle, and therefore, larger the grain size, larger will be the crater diameter. So, that for larger grain sizes, we will have something of this type. That means, overlapped large craters. So, that ultimately the surface will come out like this. So, naturally we can say that the ultimate surface roughness produced has a possibility of having higher roughness than this particular case. What will this produce? This will produce something of this type. Okay. So, we will say that the probability of this one being more rough is higher. That is what. Okay. Next is that coming back to the graph, we see that glass is having a higher surface roughness compared to tungsten carbide. Why is this so? This is because of this particular figure. Let us have a look. That is the same grit will be going into glass by this while the same grit would be going in to a much lower depth in tungsten carbide. Okay. So, that means, these two distances being different, this will produce larger craters, and that will possibly, the probability of producing higher surface roughness with larger craters is more. This will produce smaller craters. So, the probability of producing lower surface roughness with smaller size craters is more. So, that is why this is the behavior of, I mean, this is the graph of surface roughness with respect to average abrasive grit size. Coming to this one, second one is static force. If the static force is increased, we will expect the MRR to be increased by f to the power 3/4, because MRR is proportional to static force to the power 3/4. So, the theoretical graph will be continuously increasing, while the actual, that means experimental graph, we find that the MRR starts falling down after a particular period. I mean, after a particular increase in, or after a particular value has been attained by static force. Beyond that, if some increase is there in static force, the MRR comes down. This is because at higher static loads, the abrasives get crushed and MRR comes down as a consequence, because they become smaller grits and they have less ability to remove material. So, now comes static force versus MRR. We have discussed this just now. Just the effect of amplitude increase is being shown superposed on this graph. Frequency. With frequency, MRR should be having a proportional increase. However, when we actually do the experiment, we find that in the long run, that is, as frequency is increased, MRR starts falling down. This is because the average speed which has been considered due to vibration, this is not fully accurate. A gross sort of averaging has been done by dividing 4 amplitudes by the time period. That is where an error creeps in. This we had discussed last day. MRR, change of MRR with respect to lambda. Okay, that means workpiece hardness divided by tool hardness. So, if the workpiece hardness by tool hardness increases, that means workpiece becomes more and more hard relative to the tool. Therefore, the tool will take up most of the damage, and therefore, MRR will be coming down. So, that is what is reflected. Tool will be taking up more of the damage, delta T will be much higher than delta W, and therefore, MRR will come down. MRR essentially refers to the material removal rate of the workpiece. Next, average grain size goes on increasing as suggested by the MRR equation, and a theoretical value should be always proportional, but after a particular stage it is found that average grain size starts reaches a maximum and then falls. So, in the average case it is found that there is again the crushing tendency coming in. Average the grains, when they become very large in size, they have a tendency to get crushed and they have a difficulty to enter the machining zone, because they are so large in size compared to the amplitude. Boron carbide, silicon carbide, with concentration we find that MRR is increasing, but after a certain stage it stops increasing. This is because concentration to the power 1/4, I mean MRR is proportional to concentration to the power 1/4, and therefore, after a particular stage the increase in MRR with respect to concentration is not very significant, C to the power 1/4. That is why both these curves are showing a tendency to flatten after say 30% concentration has been attained. We also notice that for the same concentration, boron carbide is giving higher MRR compared to silicon carbide. What can be the difference? How is this particular difference explained by the model? The model, however, that we have studied does not take into account any of the abrasive properties. These are the two abrasives which are used. So, if these are the two abrasives used, why then should they give different MRR? Because there are no properties of abrasives in the final expression of MRR. You know, f to the power 3/4 divided by sigma w to the power 3/4 plus 1 plus lambda to the power 3/4 into amplitude to the power 3/4 into grid diameter into frequency and all those terms. There is no term of abrasive hardness or what do you call it, strength, nothing of the abrasives except abrasive size. So, material properties are not included. So, why should there be a difference? This may be due to the fact, first of all, that abrasives also undergo some kind of compression when they are pressed between the tool and the workpiece. So, that the compression being equal to delta T plus delta W is not fully correct, and also it could be that many of the grits get crushed in the process of impacts, or they undergo fatigue failure because there are so many impacts per second, and that may be affecting silicon carbide in a more drastic manner than the effect on boron carbide. Okay? That is a possible solution. Amplitude. MRR has a relation with the amplitude, like amplitude to the power 3/4. I mean, MRR is proportional to the amplitude to the power 3/4, and that is what is reflected here. Okay? If the results are taken, you know, more towards the higher values of amplitude, surely they will show a tendency to have less gradient. Now, we will quickly have a look at some of the other ultrasonic methods which are taking the help, not exactly, you know, not exactly of the same type as our ultrasonic machine, the ultrasonic typical dye sinking type machine that we are seeing. It is not exactly of that type. So, let us have a quick look what it looks like. This is the isometric view. So, there is a core, you know, tool which is rotating and it is vibrating, and there are abrasives here on the periphery. Coolant is given from inside, and external cooling is also applied like this, and therefore, in addition to this sort of vibration, we are having rotational motion as well, high speed of rotation. Some people refer to rotary ultrasonic milling as simply ultrasonic machining plus grinding, conventional grinding. How is grinding taking place? Due to, by virtue of these abrasives. What can be the, you know, advantages of this method? The advantage of this method is that over and above ordinary you know, grinding action, we can have better material removal by vibrations. Let us have a quick look to the area of application of this particular method. So, in addition to vibration, we are having rotational motion. So, ultrasonic milling, we can have a quick look. Diamond grinding plus ultrasonic machining is equal to rotary ultrasonic milling. So, those grits that we had seen, they are essentially diamond grits, diamond grinding plus ultrasonic machining. What are they good for? That is the areas of application. one big area of application is the grinding of the ultrasonic grinding of zirconia ceramic dental parts. Okay. That means these are dental part replacements, zirconia ceramic, that means zirconium oxide, titanium alloys, that means difficult to machine materials, ceramic matrix composites or CMC, glasses and ceramics in general. So, these are the areas in which rotary ultrasonic milling is resorted to. Next, we can also have hybrid processes like ultrasonic machining plus ordinary milling. What is it good for? Where is it used? It is once again used for dental implants, optics and watch parts, and tools like for example, cooling holes in tapping tools, okay, for making external internal threads. So, in those tapping tools, if you want to make cooling holes, this particular process can be used, to our advantage. There can be ultrasonic machining centers also. So, just like we have ordinary machining centers in which milling, grinding, drilling and all these operations can be carried out conventional, we can have ultrasonic machining centers in which ultrasonic milling, grinding, drilling, pocketing, rastering, light weighting of optical glasses and ceramics, these are possible, and these can be available as 3 axis, 4 axis, 5 axis for complex geometries. What do we mean by 3 axis, 4 axis, 5 axis? It means in 3 axis there will be 3 of the axis moving, x axis motion, that is workpiece with respect to the tool can be given motion in 3 axis x, y and z. In 4 axis additionally you might be having a rotary axis about a particular linear axis, and in 5 axis there will be 2 such axes. Why is this so? Let us have a quick look for this 4, 5, 6. If you have a body of this type, this side of the body is called re-entrant side. Why? Because if you have an ultrasonic tool here, and if you have 3 axis machine which can make the movements in these 3 directions. So, it can move down, the tool can move sideways. So, sideways, up, down and out of the paper into the paper. So, in no way can it reach, okay, it has no way of reaching this particular space. But in addition, if it can rotate this way, that means if it has an axis of rotation about this particular axis, in that case it can rotate and access these portions, and it can also have that ability to rotate about this axis. So, that it can rotate this way also, if it has a problem in that direction, this also it can take care of. So, 5 axis machines can machine surfaces which fold over themselves, so that they have apparently inaccessible portions. These can be reached by 4 axis and 5 axis machines. So, such machines just for ultrasonic machining, they are also available, and they are called ultrasonic machining centers. So, let us quickly go through some of the other processes which are existing as either hybrid processes or vibration or ultrasonic assisted machining processes or associated processes. So, in order to make chip removal easier, and in order to improve the quality of manufactured parts, we have basically 2 methods in which use of vibration as an assistance is used. One is called modulation assisted machining, in which the range of frequency is generally up to 1000 hertz, that means 1 kilohertz, and the amplitudes are up to 500 microns. That is quite a large value indeed. Okay. And this improves the efficiency and process capability in precision machining processes. However, this is not exactly the machining. In ultrasonic assisted machining, the frequency can go up to 40 kilohertz, okay, 40 kilohertz, and the amplitudes are generally between, they are much lower, generally between 3 to 30 microns, okay, and it helps in high precision machining and machining of difficult to cut alloys and brittle materials, difficult to cut alloys and brittle materials. And generally ultrasonic assistance is in turning and drilling. Chemically assisted ultrasonic vibration machining, okay, chemically assisted. How can we assist? First of all, why do we need this assistance in ultrasonic machining? Ultrasonic machining is associated with two distinct problems. One is that the material removal rate is not very high. Material removal rate is not very high, and the surface roughness is also not very high, because it directly corresponds to the average grit size. So, what is the way in which this can be solved? One way of solving this is to use some acidic medium, which will be chemically removing parts of the work surface which is not touched by the abrasive grits. That means, those places where abrasive grit action has not taken place. Normally, when abrasives are impacting, there will be some upraised portions where the abrasive has not hit, and they will be defining the surface roughness. So, simply if we put some acidic medium which eats away those portions, we will have a much smoother surface. So, hydrofluoric acid is known to attack glasses, etc. So, a common practice is in chemically assisted vibration, ultrasonic vibration machining, to add some hydrofluoric acid into the alumina slurry, and in that case material removal also gets enhanced, because chemical action associated with ultrasonic vibration greatly enhances the material removal rate. In some cases, even 200% increase in material removal rate has been noted. So, when hydrofluoric acid is added, higher material removal is obtained, better surface finish is obtained, and forces in between the workpiece and the and the vibrating horn, they also come down drastically. However, if the concentration of HF is more than 5%, it may result in enlargement of the entry point of the hole which is being drilled, and therefore, concentration has to be kept within limits. So, before we formally enter the 10th lecture, I will just take one or two problems that we had left unsolved from the previous questions and quickly have a go at it. So, suppose you are making and selling USM machined mementos. This was one problem which I had set for you for solving, and since we are getting some time, I will quickly have a look at it for solution. you are making and selling USM machine mementos on imported glass when the price of imported glass samples become rupees 400 from rupees 200. You have the options to use Indian glass samples which are rupees 250. So, you will be saving from the material side 150 rupees now if you use Indian glass and keep the machining the same. That means, you keep the machining the same and you use Indian glass, and machining rate is rupees 300 per sample. Okay. So, quickly you can say, okay, rupees 350 plus 300 makes 550 rupees, or we can use the imported glass rupees 400 and double the dead weight, defining the static load. If man machine hour rate and abrasive cost per hour are 200 and 400 respectively, what's this? Man machine hour rate and abrasive cost per hour is 200 and 400, that means 600 per hour. Okay, 600 rupees per hour. Find the, what are we to find? Okay, so we have to choose from these multiple choices. So, if man machine hour rate and abrasive cost together, they make 600 rupees per hour. Then first one is E makes a saving of rupees 28 over B. E is what? A is Indian glass and B is imported glass. So, 550 rupees must be the cost of Indian memento. Let us now calculate what is the cost of producing an imported glass memento. So, that we can let us quickly see, makes a saving of rupees 28, and next option is B makes a saving of rupees 28 over A, and A saves around rupees 90 compared to B, none of the others. Okay. So, let us quickly calculate. First of all, we may notice that cost of manufacture for foreign make is equal to 400 rupees raw material plus making charge. What will be the making charge? Cost of manufacture for Indian make is 250 rupees plus 300 rupees. This we had done orally just a few minutes back. So, 550 rupees is the Indian. So, per hour making charge is equal to rupees 600. So, the standard weight must be resulting in 30 minutes of machining time. So, standard weight, this term is slightly misleading. It means that if per hour we are having a making charge of 600 rupees and if the Indian make requires 300 rupees, so it must be 30 minutes of machining. Okay. So, 30 minutes of machining must be required in case of the Indian make. Hence, the material to be removed in 30 minutes is equal to K into standard weight. Oh, I understand. Standard weight here means the standard static load that we are using. So, if the material to be removed in 30 minutes, that means material removal rate must be proportional to K into static load to the power 3/4. This is understood, no problem. So, from here, okay, we can get an estimate of the imported glass machining time. Let it be T minutes. Therefore, in the second case, material to be removed in T minutes, okay, in T minutes is equal to K into twice the standard weight to the power 3/4. Why are we doing this? Because we are saying in the second case we are increasing for imported glass. For imported glass, we double the dead weight. Okay, we double the dead weight. So, in that case, the equation must be material removal rate, where we are taking basically T minutes for the time of manufacture, equal to K into twice the standard weight to the power 3/4. After this, from this, as in the previous problem, T will come out to be 17.838. I have foregone the rigorous calculation, but as you can notice here, from here we will find out the value of K in terms of standard weight. that is K is equal to MRR divided by 30 into standard weight divided by standard weight to the power 3/4, and we will put the value of K here and easily find out the value of T. Okay. I am sure you can, I will write it down, but you can solve it yourselves. So, look at this, we have here in the first case MRR by 30, MR material removed by 30 is equal to K into F to the power 3/4. Therefore, K must be equal to MR by 30 into 1 by F to the power 3/4. K is found out. In the next relation, we have MRR by T is equal to K into twice F to the power 3/4, which means that T is equal to, if we divide this one, once again this is MR, if we divide this, which one should we divide? Okay, if we divide this with this, let us see what we get. We get T cancels out. So, we get MR cancels out, we are dividing it. So, T by 30 is equal to K cancels out, F by 3/4 divided by 2 by 3/4 into F by 3/4. Okay. So, this one cancels with this and T becomes equal to 30 divided by 2 to the power 3/4. This is a pure number which you can easily calculate, and this will come to be roughly 17.838. Coming back to the question, So, if it is 17.838, we can quickly calculate the making charge as 600 divided by 60 into 17.838, which comes to be 178.38. So, that the imported costs come out to be 400 plus 178.38 equal to 578.38, and therefore, it is 28 rupees roughly more than 550 rupees. Okay. Therefore, A is the answer. Let us see. A makes a saving of rupees 28 over B. So, A is the answer. Thank you very much. Thank you.